In this lecture, we're going to discuss some implementation details regarding convolutional neural networks and also how to analyze the results. We're going to talk about details about how to get code working and how to interpret what's going on while you're doing that. Here's our neural network, and we've been talking about the different components of it. And then last class, we talked about this process, these red arrows. How do you minimize this cost function L with respect to the weights? How does TensorFlow do that? I hope everyone has at least a rough idea of how that happens, high level understanding of how that happens. But we know that when you press enter, TensorFlow is creating this connected graph of your defined equations using the implicit gradients in each node in that graph that are hard-coded into TensorFlow, and then passing that gradient information back and forth. In the forward pass, it's just evaluating all the terms, saving them. In the backwards pass, it's multiplying gradients to then update the tf.variables, the weights that you defined in your code. Okay. Really what we're going to talk more about in this lecture are these other specifics, and then we'll talk about how to monitor your code and make sure it is converging. TensorFlow is a nonlinear optimization process, and in general does require maintenance or feedback. It's like having a small puppy, and you can't just leave it and think everything's going to be okay. You'll come back and it'll have torn up your room, right? All this stuff in your room or whatever. And so you need to be around and watch it and make sure it's doing a good enough job, and then you have to coax it to do better and better. Okay, so focusing on these other specifics down at the bottom, what are some additional methods or tools you have at your disposal to make sure your TensorFlow experience is going well or optimal? In general, this slide I think does a nice job in summarizing the mindset that you should have when trying to make your machine learning code work. You want to think of the general problem of creating an effective neural network, training a neural network. So what that means is you are generally presented with a small training data set, certainly in this class in the homeworks, but also for your final project. We unfortunately don't have the resources of Google at our disposal. You are going to be constrained, and so you'll only have a limited training data set. And what happens in that scenario is you will overfit your training process. You'll hit enter, it'll train, and then when you test your data, it'll do terrible. So to avoid that issue, or to work your way out of that issue, you want to use regularization. So regularization is a blanket term. There's many things you can try to regularize your training process. In this slide essentially says you want to add some randomness. There's lots of examples of adding randomness to training, but the idea, the mental picture you should have is having a network that you're pushing in different directions during training, perturbing a little bit so that it's not getting it stuck in this very tight overfitting scenario, but instead is smoothed out a bit. And then when you test, you can go ahead and integrate over that randomness. So mathematically speaking, you are not just establishing a function that maps your inputs to your outputs f, it's also taking as input a random variable z. And that random variable z can be integrated out during actual testing by appropriate methodologies. Namely, just considering a bunch of examples and averaging the performance is the easiest. But if you're really getting into the details, there's other tools that you can use, which we won't really cover in this class. You are going to use dropout and data augmentation, most likely, in your final project. And there's many other examples that we're not going to cover in this class. Here I'm just listing a few. But if you are interested in this, it's the bread and butter of current machine learning research, is how do you effectively regularize neural networks? Right? How do you make them work repeatedly in a trusted manner, right? Is another way to put this. and generalize not just outside of training to testing data, but potentially to other contexts as well. Okay, so data augmentation, we already saw this. This is a simple form of randomness that you can introduce. You have a bunch of training data, randomly perturb that data itself in known ways that will mimic what might be encountered. In your final project, you can think about this as like a kind of simple way into simulating your imaging system. If you are comfortable doing data augmentation, changing the image of the color, rotating it, scaling it, you are already thinking about indirectly ways to mimic or simulate an imaging system, right? Here, that's an imaging system with an orange filter placed over the lens, right? That's an imaging system that's been flipped upside down. The sheared one has been rotated a little, right? So you are already beginning to think of geometric transformations to your imaging. So the next step, you can start to blur these images, right? Then you're mimicking a blurred camera, right? You can then blur it a particular way. Then you're mimicking a particular lens design that has this type of blur within it, right? You can begin to manipulate these images at the pixel level, and then you're simulating or altering properties of the image sensor itself, turning off different pixels or changing their color. So those are all easy things to throw in directly before you start developing your neural network code. So another regularization we saw is batch normalization. This happens under the hood. I'm not going to dwell on it, but we already spoke about it. Dropout is another form of regularization that also you can easily add in with a single line of code. This process sets certain neurons to 0, effectively does not update them or use them, and doesn't use them in the forward pass, and then sets them to 0 in the gradient update randomly. So at iteration I, let's say neuron 7 will be turned off. It won't be used. It'll be set to 0 in the prediction of that particular image during training, and it won't be updated at all. And then the next iteration, it'll be turned on probably, but this one will be turned off, neuron 8, right, for example. And then that continues to happen thousands and thousands of times. So every weight will be updated many times, but half the time they won't be randomly selected. And so let's look at our code real quick to see those features. We're gonna look at the input. We're gonna look at how we're splitting the data. We're gonna look at our cost function. We're gonna look at the optimization method, batch size, augmentation, and dropout. So this is the same code example that we went over before, but I'm just gonna quickly highlight these features. So first is the structure of the input. So then immediately we're splitting the training and testing data. So this is good practice, right at the download process. Training and testing is split. You don't have to do it at the exact same line you're downloading the data from, but as early as possible, because then you won't mix it up. But you can see our normalization, right? We talked about how it's important to normalize the image data up front, but the first step is to normalize it to between 0 and 1. And then we are mean subtracting it and dividing by its standard deviation. Okay? So I don't know if that divide by 255 is even necessary if you're doing this step here, but essentially this is where my cursor is the important one. It needs to be 0 centered, right? We don't want the data way off away from 0, because then when it hits our nonlinearities, they won't be effective. They won't be effective both in the evaluation, giving diversity to our data passing through, nor in the gradients, because the gradients of most nonlinear functions are 0 at large values. Okay, and so that's the normalization process. And then here's our model. Here's our batch size. This is something that just specifies the number of images that are being considered during each iterative update. When TensorFlow does a forward pass, it'll pass all 32 of these images in this batch in. The batch is selected randomly or pseudo-randomly. So it won't go in sequence, it won't go in order, but it'll grab 32 images, but it'll do so in a way that each time it goes to the next batch, we'll grab 32 unique images. Because in one epoch, the goal is to have all images have gone through your network once. And so there are ways, I'm sure, to say, hey, TensorFlow, don't go randomly with your batch, go in sequence, for example. And then I'm sure there's other ways to say, hey, I don't care about making sure every image is seen once per epoch. You can just randomly grab. If you really are idealizing randomness in your process, that's fine. So here's our dropout. It's that easy to include dropout, that process of randomly setting certain weights to 0 during the evaluative step and then not updating them with the gradient step. Okay, so it's a single line that you could add to your code, and we already discussed how you want to add it after these dense layers, after a fully connected layer, which is .dense in the code. So we have just training and testing. And so if I wanted to make a validation data set, I would go ahead and need to take generally my training set and do an additional split. And so this mnist.load data, you'll notice, is a prepackaged function that has its own train test breakdown percentage. I think it's something like 2080. I forget. But you can go ahead and define that yourself. If you don't want to use this, you won't be using a load data function probably, so you'll have to create code yourself that goes in and sets aside images for training and testing, right? And some of you will have the flexibility to do that randomly. Each time you try it, it can be a random new breakdown of training and testing. Or some others, it'll have to be fixed, probably because you really don't have enough data. And you just want to say, okay, that's always going to be my testing data. Cool. So this is kind of what you'll see. You can use different ways to plot the training, testing error, but you should definitely always do that. Per iteration, you should be able to observe how the training loss is going down. It will almost always go down. You'll sometimes see training loss plots that are noisier versus smooth. It depends on the type of descent method you're using. Atom, for example, will be generally smooth compared to a steepest descent approach, which will be jumpier. And that's because the jumpiness is caused by overshooting local minima and generally going up and down as it goes down the hill, so to speak, depending on the step size. But generally, this will be not the problem that you will encounter. And of course, you'll see the training loss go down to a certain value and plateau as a function of iteration. That's to be expected, right? The goal then is to get this lower and lower, right? Here it plateaued at something like 1.5 arbitrary units, and maybe your goal is to get that down to 0.5. Or maybe it isn't, right? That's something you really have to figure out when you look at your test data, which I'll show next. But you have a number of choices there. Instead of using atom optimization, you can use another optimizer, right? We talked about that. The step size is a critical parameter. So all of the optimizers in TensorFlow have a default step size. You need to go in and modify that. And it's highly influential in the optimization process. That step size number can really make or break things working well. So that's probably the number one thing you should change, right? So for example, Atom's default step size, I'm pretty sure, is 1e to the negative 4. And if you change that by a factor of 5 or 10 in either direction, it will substantially change how the network is behaving. So when in the first kind of, this isn't working stages, simply change that number and maybe you'll get lucky and things will start working well. This is what you'll have to begin to do to make sure things are really working. Oftentimes I see in final projects that people don't even really make it to this stage in time. They leave this off until the last minute and then nothing really works, okay? So don't get stuck over here just looking at training, because it doesn't matter really how low this goes. It could just be completely overfitting and not generalize at all to your test data. Right? And so you really have to just use this as a guide to say it's roughly working. Let's check the validation data. Right? So what you can see in the validation data is that the algorithm is actually working better and better. That's a great plot to encounter. If you see something like that, you should jump around and be happy. Right? because as you continue iterations, you're seeing training improving, which is always great. It's not the end-all be-all, but that's not bad news. But most importantly, the validation accuracy, the accuracy that network is seeing as it's trying to test the network on unseen data, is getting better and better, right? And so this would be like, let's say, a binary classification task. I know that because it's starting off with random performance, and so that would 0.5 is just flipping a coin. If it was like a 5-category classification task, the accuracy at iteration 0 would be 0.2, right? And so you're already at 0.55 in a very noiseless way, right? You can visually tell that because there's at least 30 points there, that there is a statistical confidence that you can assign to this process of improved validation assessment. And so this is great because even though the accuracy is low, you've only gone up to 0.55, 55% chance of being right. You just need to wait longer and it'll get better and better. And that's a great place to be in, right? You just hit enter and go to sleep. And then wake up, and hopefully that orange curve will be up at 0.9. So how can you help encourage this process of having the validation accuracy go up even more, right? In an ideal world, where would that orange line be? What's the best thing you could ever expect? Slightly lower than the blue line. You can never expect the orange line to be up here. It will never go there. Because the network has access to all of this data. How could it possibly do better with data it hasn't seen? So, this gap between the orange and blue lines we've talked about, it's called the generalization gap, right? It has to do with this variance bias trade-off we discussed. And it is essentially the bias term. So to address the generalization gap, we can use regularization. So these procedures I discussed before, if you start adding in dropout layers, if you start adding in more data augmentation, for example, you should hopefully then observe this orange line go up even more. It won't go down if you add more regularization, these random perturbations to your network. So these plots you should definitely use to your advantage during your homeworks and your final project, if you haven't been doing so yet. Something you will see if you then did what I suggested and saw the orange line going up, which hopefully you all will be fortunate enough to experience, and you then say, I'm going to go to sleep and let this run overnight, is you'll see an orange line like on the right. The validation error will go up and up to a point, and then it'll start to go back down if you iterate too long. That's when overfitting begins. What you can do in that scenario, don't worry about that. It's not a big deal. You just say, hey, when I do my final training to test my network, I'm simply going to make sure I just iterate to here. This was, let's say, 1,000 iterations. I'm not going to do 2,000. I'm just going to do 1,000. Why? Because I used my validation data to figure out that the ideal number of iterations I should employ is 1,000. Because if I do that, then hopefully my test performance will be as high as possible. All right, and so that's really the best you could ever hope for, is if you go ahead and train, validation going up, you let it go up until it starts to go back down, and then you freeze your iterations at that peak and train the network again and throw your test data in and cross your fingers, right? Or what some people do is during this process, they're training their network, they're saving their weights at many epochs. And then they'll use the weights at a certain epoch as their final network for testing. So early stopping is this idea of picking a particular iteration to train your network to for your final test. That will get you, especially in this final project setting where you have a smaller data set, will definitely help you get good performance compared to picking a random iteration. But for those of you who are using these methods or plan to for your research, that is a nice way to eke out an extra 5% performance gain for free, right? Just by thinking about that. A second trick you can use to eke out an extra couple percent performance gain is something called mode ensembles or model ensembles. What this approach does is it essentially uses computation to help you trade off the need to use your computer a lot more to then get slightly better performance. The procedure works as follows. You say, hey, I have a network that's working pretty well. It's not great, but I'm happy. Let's say it's classifying cats and dogs with 90% accuracy. You then say, hey, I'm going to take that process of creating that model. I'll create 100 of them. I'm going to independently train 100 of these models. Then what you do when you want to test your data is you don't just use one of those models, you use all 100 of them. You pass your test data through each of those models. Each one, let's say for one particular image of dog, like dog image N. Let's say 60 of them say it's a dog and 40 of them say a cat. You use a vote. You take the mode of the output, or what's called a majority vote. If 60 say it's a dog and 40 say it's a cat, then it's a dog. If 51 say a dog and 49 say a cat, you're still going to guess dog, right? You're essentially using 100 models to vote on their best choice as opposed to just having one network tell you its vote. Right? That process of voting is a similar form of regularization. Because each network was randomly initialized, it will arrive at a unique local minimum. You're essentially averaging over all those local minimum in that voting process to pick the best suggested result by a group of 100 experts as opposed to a single expert. Right? Experts being your trained networks, which are obviously not experts, but you get the idea. So in one of the first papers I wrote in this space about deep learning, I did this, and it was definitely like over 5% in performance gain. It was really helpful to do that. Something else that we'll talk more and more about is harder to do. The reason why I'm saying that is because a number of groups in the past have attempted to use this technique, transfer learning, in their final projects and ended up really struggling due to various technical issues that prevented them from getting as much as they could out of it. But if you do succeed in some of the technical challenges associated with transfer learning, it can be quite helpful. I should say that. What we've already discussed a few lectures ago is that the earlier stages of a deep neural network generally converge to weights that have some sort of structural properties, right? Similar to the earlier stages of our vision system, for example, where various stripes and other wavelet type features are used to convolve across the images that are coming into our eye to then result in subsequent values that are more useful for our visual system processing than just the raw pixel values. What that means is these earlier weights down here, no matter what data you're inputting, will generally converge to similar type weights. Right? The earlier stages of a neural network generally are image data agnostic, because all image data generally has these structural properties that at a high level are shared. So what you can do is download these weights. And in the extreme case, you can download all of the earlier stages of a convolutional neural network's weights, and then only really alter the final weights in the last couple layers of fully connected matrices. And so that basic idea is called transfer learning. It has many different flavors and implementations, but it is a useful strategy if you really have very limited image data. If you are struggling with getting your limited data set that you might be using to work in whatever context, then you can download a pre-trained network. In TensorFlow, there's a few lines you can add to freeze certain weights, right? It effectively involves removing the tf.variable and just having it be a tf.constant. And then you only will train certain layers. So that process, again, I've seen it be successful. I've also seen it not be successful. If you feel comfortable with trying this and you feel like you have some experience with TensorFlow, then this is a great thing to give a shot. If you're not that comfortable with it or you try this, let's just say if you do end up trying this and it's really a struggle, just remember what I said. It is challenging at times due to various programmatic reasons, and so maybe you shouldn't pursue that direction. If you do pursue that approach, it's not too surprising that the amount of weights you want to utilize that are saved, that you're not going to train, will depend on how similar the data is that you have to the data that was used to train those weights. And so if you are using very kind of conventional image data, like one would capture from a camera, then you can use data sets like ImageNet, which are just regular pictures, fill most of these early layers, right? Because structurally speaking, your image data and the ImageNet data set are relatively similar. And so you could just freeze the last layers to do a linear classifier or a single fully connected layer, for example. If you do have little data and a very different data set than what you might be able to pre-train with, you're in trouble. You need to find a data set that closely matches your data set, right? And so if you are using MRI data, there's definitely pre-trained networks out there that have used MRI data. It might not be exactly the same as your MRI data, but for these earlier layers, all of that, you normalize the data appropriately and account for these different things that can impact the results, the total number of bits in each DICOM image, which is the image file type for MRI, then things can work decently, even though it's a different MRI scanner. Because MRI image data is like a very specific type of image data. If you see an MRI, hey, that's an MRI, right? Generally speaking. Same thing with CT or ultrasound, right? And so if you have an ultrasound data set and you say, hey, I'm going to use ImageNet to pre-train or to do transfer learning, that's a problem. And you have very little data, then you're in the upper right-hand corner. Why? Because regular camera images are pretty different than ultrasound images. And maybe these layers will be okay, but these ones won't. And then you'll end up with some weird performance that's hard to figure out. We'll talk about object detection in maybe 3 or 4 classes. But object detection, fundamentally, every object detection pipeline you'll use will have frozen weights that have been pre-trained on ImageNet or some other very large image data set. Those will be then used to help you find where objects are, to create bounding boxes, or rather candidates for where objects are, bounding box candidates, that you will then fine-tune, is the term, or use your training data to help refine and make better. Right. So in other words, these weights you can download for early layers of convolutional neural networks aren't just used to help you create your classification networks. They also are used as building blocks for more complex tasks like object detection or segmentation or object tracking, which is the more challenging problem of following a single object, i.e. person, in a crowd of 10 people in a video, for example, and not mixing it up with another person. All right, so all of those are machine deep learning goals, but they don't rely on having this type of convolution to a classification decision, yet you can use all of those weights that have been used to classify images as your early layers to help you manipulate the pixels to get them into a space that then is well suited for subsequent optimization. Sound good? So it really is the norm at this point to use transfer learning, even though it's maybe not so well defined because its uses are so pervasive. All right, so then what are some other tricks? So this is more advanced. Most of you all won't have time to do this for your final project, but there are tons of hyperparameters that we've already seen Hyperparameters are the little numbers in purple, generally, that are up to you, right? That's the easiest way to define them. Maybe a better dropout rate is 0.4, not 0.5. Maybe a better learning rate is 1.7 e to the negative 3, not 1 e to the negative 3, right? All of these little variables can impact your final performance, and you want to avoid just tweaking them a little bit repeatedly to get a little bit better performance, because you just want to get something working for your final project. But if you're doing research, then that's a great thing to try to optimize to eke out better and better performance for the paper you're going to write. So a great way to do that is a brute force search. There's many other methods that have been developed, and brute force searching just still works. So I use brute force search. It's easier. If you have 10 parameters, then create up in your GPU cluster, which hopefully you can get access to eventually if you start really doing research in this space. Create 10 for loops and run through 20 values for each, and then see how well they do, and then use that to refine a next attempt where you say, okay, I'm going to pick those 3 values here, those 3 values here, those 3 values here, and then let's holistically try again. And maybe after 2 weeks, you've settled on some really good parameters that are much better than what you started off with. The other approaches out there, there's a ton. The general field's called meta-learning. That means you're learning how to learn. And so what that involves typically is, instead of brute force searching through these little variables like the dropout rate or your step size, things like that, those become weights as well, and those are learned on the fly. It doesn't work. I'm not a big fan of meta-learning. You can write papers about it and everyone gets excited. So it sounds cool, because it's like getting to this whatever artificial intelligence goal or whatever, but it just doesn't work. Maybe it will in the future. TensorFlow has a TensorBoard feature, which is really useful. TensorBoard gives you this plotting ability. It gives you the ability to show your training as a line with different steps, your validation, etc. It's pretty nice. This is an older screenshot from it. I would imagine it's gotten even better. You have various graphing options, and so you should really take advantage of this, not just for creating summaries of your data for the research paper you're supposed to write or to show stuff during your homework, but also as you're training. You can watch this. It updates in real time, right? So then you can see, oh, it's definitely not working. I'm going to stop. I'm not going to waste an hour, and etc. Okay, and so that gets us to how to examine and present our results, and we'll cover this next class. This is really what you all need to hopefully converge towards to present how well your network did when it's done. And so these statistics, I'll just show them right here. If you read papers about machine learning, I'm sure you'll in the future see these terms. If you stay in engineering, it's almost unavoidable now to not hear precision recall or confusion matrix, etc., because machine learning is becoming so pervasive in helping us analyze our data. And these are the standard methods of reporting how well you did. Okay? All right, thanks everyone.